With a Boolean variable, well, we only need 1 byte of memory. That's why the distance between the memory address of age and student is only 1. 40 minus 39 is 1. Integers take up 4 bytes of memory. 44 minus 40 is 4 bytes. So that's an introduction to memory addresses. It's going to be helpful in the next topic when we discuss pointers. If you would like a copy of this code, I'll post this in the comment section down below, and that is an introduction to memory addresses in C++. Alright everybody, so I'm going to explain the differences between pass-by-value and pass-by-reference. In this example, we'll swap two variables. Suppose we have two imaginary cups. I'll name the first cup X. X will contain Kool-Aid. Then we have cup Y, which contains water. I need to swap these two values. We'll need the help of a temporary variable, string temp. To swap two variables, we would assign temp equal to X, X equals Y, Y equals temp. Let's display these variables. Standard output, X, the variable X. I'll add a new line. Let's copy this, paste it. Y, the variable Y. This should work. X now contains water, Y contains Kool-Aid. Now check this out. What if we create a function to swap two variables for us? The return type will be void. I'll name this function swap. There will be two parameters. String X, string Y. Let's copy this section of code, delete it, then paste it within the swap function. Then you'll need a function declaration at the top of your program. Then we will invoke this function. Swap, pass our arguments, X and Y. Let's see what happens. Okay, what the heck? X still contains Kool-Aid, Y still contains water. These values weren't switched within my variables X and Y, even though we invoked this function. So why didn't it work? Well, that's because normally when we pass a variable to a function, we're passing by value. When we invoke this function, we're creating copies of the original values. What we have now are two copies of the variable X and Y, and all we're doing is switching the two copies and not the original values. So that's pass by value. We're creating copies of the arguments. If I need to change the original values of these variables, I could instead pass by reference. A reference as in a memory address. An address in your computer's memory where a value is located. I will prefix the address of operator, which is an ampersand, to these parameter names. Then add that to your function declaration as well. Now let's see what happens. Yeah, those two variables were switched. X contains water, Y contains Kool-Aid. When we passed by value, we created copies of X and Y. With the parameters, when we use the address of operator, we're passing memory addresses to where the original X and Y variables are located, and then swapping the values. Just to reinforce this idea, let's revert to passing by value. I'm going to display the address of X and Y. Then within our swap function, let's get rid of this code. Then I will also display the addresses of X and Y. See, we have 4 different addresses. Our original X variable has a different memory address than the one that's within the function. Same thing goes with Y. These two addresses are different. We have 2 X variables and 2 Y variables. Originally within that swap function, we were switching the values of the X and Y copies. If we instead pass by reference, let's use that address of operator again. Well, now X and Y are referring to the same place. They have the same memory addresses. That's why the swap function worked when we passed by reference in place of pass by value. So that's the main difference between pass by value and pass by reference. You should use pass by reference as often as possible, unless you have a reason to pass by value. If you would like a copy of this code, I'll post this in the comment section down below. And well, yeah, that's the main difference between pass by value and pass by reference in C++. Hey everyone, in this topic I'm going to explain const parameters. A const parameter is a parameter that is modified with a const keyword. That makes it effectively read-only. There's a couple reasons why you might want to declare a const parameter. Your code is more secure within a function, and it conveys the intent to other programmers. It's especially useful for references and pointers. Here's an example of const parameters in action. I have standard string name, assign your first name, then int age, whatever your age is. Then suppose I have a function to print my info, void print info, and there will be two parameters, standard string name, int age. Be sure to add a function declaration if you're missing it. Then if I need to call this function, I would invoke the function name, pass in my arguments, name, age. Then we can print our info. Standard output name, standard output age. This, of course, does what you expect. It prints our name and our age. To make this function more secure, we can instead use const parameters. That means that we can't change the values that we receive, name and age in this case. Just as a test, let's set name equal to an empty space and age equals 0. I don't want this to be able to happen at all. Now when I run this, we don't have a name and we don't have an age. To make these parameters read-only, we can precede the parameters with that const keyword, const string name, const int age. And you would probably want to add that to your function declaration as well, just to display intent. There, we have an error. Assignment of read-only parameter. Age and name is somewhere up here, but I don't feel like reading all of that. When we pass our string and our integer as arguments, what we're doing is effectively making a copy of name and age. Technically, we're not modifying the original variables. In this case, using the const keyword when we pass a variable by value isn't really that big of a deal, but it at least conveys intent. If we were working with reference data types, now we'll pass by reference. Well, now it's a bigger deal. We don't want anybody modifying the original name and age variables. Alright everybody, those are const parameters. They are parameters modified by the const keyword that effectively make them read-only. Within a function, your code is more secure, and it conveys intent. It tells other programmers, hey, don't mess with these values. They're useful with references so that nobody can change the value found at that reference. Then in the case of pointers, nobody can change the address of where a pointer is pointing to. So yeah, those are const parameters in C++. Hey everybody, in this topic we're going to create a program to validate if a credit card number is valid or not. To do so, we'll need to utilize the Loon algorithm, which I've broken into these steps. If you need some test credit card numbers, you can always Google them. I found a bunch on this website. Let's just take this one for example. And to make this more readable, I'll divide this number into groups of 4. Step 1, we double every second digit from right to left. If the doubled number is 2 digits, split them. I'm only concerned with every second digit from right to left, so we can eliminate some of these that we won't be using. Then we're going to double these numbers. So 2 doubled is 4, 9 doubled is 18. Since we have the number 18, that's 2 digits. We need to split them. We'll split 18 to 1 and 8. Then 6 doubled is 12. We'll split that. Step 2, we need to add all of these numbers together to create a sum. The sum is 29. Step 3, add all odd number digits from right to left with the original number. So now we're only concerned with the odd numbers. Then we just add these numbers together. No need to double them. The sum is 21. Step 4, we sum the results of steps 2 and steps 3. 29 plus 21, that equals 50. Step 5, if step 4 is divisible by 10, that number is valid. We could say our result, modulus 10. If that number is divisible by 0, that number is valid. 50 is divisible by 10, so that number is valid. We'll create a program that will do all of this for us. Let's create our functions. We'll need 3. Int get digit. The parameter will be a constant integer that I will name number. Int will need to sum the odd digits. The parameter is const standard string card number. Let's copy this, paste it, sum even digits. The parameter is the same. Let's copy these functions and add some declarations. We do need to return something, otherwise we'll get a warning. For the time being, I'm just going to return 0 as a placeholder. Okay, let's begin with the main function. We'll need a credit card number. That will be a string. Standard string card number. Then int result, and I will set that equal to 0 right away. We'll prompt the user to enter in their credit card number. Standard output. Enter a credit card number. Standard input. Card number. Result equals, we'll invoke the sum even digits function. Pass in our card number. Plus sum odd digits. Pass in our card number. We'll need to fill in these functions. Let's begin with sum even digits. We can get rid of this. I'll create a local variable named sum to keep track of the sum. What we'll need to do is iterate over our card number in reverse order. We can treat a string as an array of characters, and we can iterate over that. So we'll need a for loop. And we will iterate over this card number in reverse order, starting from the end. We'll need an index, int I, equals. Then we'll need to find the size of our card number. There's a built-in function for that. Card number dot size. Now arrays, they always start with 0, so we're going to subtract 1. However, if we're summing the even digits, beginning from the right, we'll need the second to last digit. So that would actually be -2. The very last digit would be -1. Our index I will begin from the second to last position. I would like to continue this for loop as long as I is less than or equal to 0. Then we will decrement I by 2. I minus equals 2, because we need every even digit. So we will take sum plus equals, then invoke the getDigit function. GetDigit. Within the getDigit function, as an argument, we're going to pass in card number at index of I times 2. However, there's one more thing that we'll need to do. With card number at index of I, we will subtract the character 0. And here's why. We're currently working with a string of characters. You can also treat a string as an array of characters. Each character, according to the ASCII table, has an associated integer value, a decimal value. If I'm passing one of these characters as an argument to my getDigit function, we'll treat that character as if it was its decimal equivalent. According to the ASCII table, the character 0 has a decimal value of 48. The character 1 is 49, 2 is 50, then all the way up to 9, which has a decimal value of 57. So if I'm passing in the character at index of I, what we'll end up working with is the decimal representation of that character. If we subtract the character 0, or its equivalent, 48, that would give us a range of numbers 0 through 9. For example, the decimal equivalent of the character 9 is 57. 57 minus 48 would be 9. You could subtract either 48 or the character 0. That would give us numbers 0 through 9, according to the ASCII table. Then we're multiplying that number by 2. Then at the end, we will return whatever the sum is. Let's fill in this getDigit function. Within the getDigit function, the digit that we're working with was doubled. Whatever number we passed in, it may take 2 digits. For example, like 9 times 2 is 18. We need to split those two numbers to get 1 and 8. So I'm going to return number modulus 10 plus number divided by 10 modulus 10. That will split the two numbers. For example, let's say our number that we're passing in as an argument is 18. 9 times 2. 18 modulus 10 would give us 8. 18 divided by 10, that would give us 1, since we're using integer division. 1 modulus 10 is 1. 8 plus 1 is 9. Then we're just returning that number, 9. Okay, that is the getDigit function. Then we need to sum the odd digits. And really, we could just copy all of this, then paste it. But there's a couple changes to make. Int I equals card number dot size function minus 1. We need to begin at the end. And then sum plus equals card number minus 0. When summing the odd digits, there's no need to double the odd digits. That's only with the even digits. And that is all the functions. Let's close out of these. So we'll have a result, the sum of the even digits plus the sum of the odd digits. If result is divisible by 10, that number is valid. If result modulus 10 is equal to 0, then that number is valid. Standard output, card number is valid. Else, card number is not valid. Okay, let's try this. I'm going to enter in that original number that we worked with, that Discover card. Okay, enter a credit card number. I'm going to paste this, hit enter. That number is valid. Let's try that again. So I'm going to enter in the same card number, except I'll add 1 to the end. That number is not valid. Hey, if you have your own credit cards, feel free to try them too and see if it works. All right, everybody, that is a credit card validation program mostly for practice. If you would like a copy of this code, I'll post this in the comments section down below. Please be sure that you do not enter in your own credit card into the comments section. And well, yeah, that is a credit card validation program using C++. All right, everybody, we finally made it to pointers. A pointer is just a variable that stores a memory address of another variable. That's it. The reason that we use pointers is because, well, sometimes it's just easier to work with an address. Here's an example. I have a stack of maybe 20 pizzas that I'm going to give out for free to my neighborhood. Instead of going around house to house carrying the free pizza and handing it out, it's a lot easier to go door to door and tell people where the pizza is located. Hey, there's free pizza at my house at this address. Come and get some. And that's one of the uses of pointers. Sometimes it's easier to just work with an address. I'll tell people where the free pizza is, rather than carry it around with me. So when working with pointers, we'll need to use the address of operator, which is an ampersand, as well as the dereference operator, which is an asterisk. Let's begin with the name. I'll create a pointer to a name. Standard string name. Assign your first name. Then we'll create a pointer to name. Where is my name located in my computer's memory? To create a pointer, it should be of the same data type as the variable it's pointing to. I'm creating a pointer to a string. This pointer will be of the string data type. Then type asterisk, that dereference operator. Then a common naming convention for pointers is you type P, then the variable name. But I'm going to make the first letter uppercase. I will set this pointer equal to the address of that name variable. And there we go, we have a pointer. So if I was to display this pointer, standard output, p name, my pointer contains this value. It contains a memory address as its value. To access the value at this address, you would use the dereference operator. I'm accessing the value of that address that's stored within this pointer, which contains my first name. By using this dereference operator, I'm accessing the value that's at this given address, which contains my first name. Let's create a couple other pointers. Let's create a variable age, int age equals make up some age. I'll create a pointer to age. The data type of the pointer should be the same as the variable. Int dereference operator p age equals the address of age. Then let's display whatever value is located at the address that's stored within my pointer of page. So we have my first name and then an age. I think I'm just going to add a new line real quick. Going back to that analogy with the free pizzas, I'll create an array of strings. I'll name this array free pizzas. I'll give this a size of 5. We have pizza 1, pizza 2, pizza 3, pizza 4, then pizza 5. Like I said in my example, it's a lot easier instead of carrying around 5 free pizzas house to house, giving away pizza. I can just tell people where the pizza is located. I'll give them an address. I'll create a pointer to this array. We'll use the same data type. We're storing strings. Dereference operator, p, free pizzas. Now I'm going to attempt to set this to the address of free pizzas. Now we're going to run into a problem. My array is already an address, so I don't need to use the address of operator. Let me demonstrate. I will display cout free pizzas. When accessing my array free pizzas, it's already a memory address. If I display the value contained within my pointer to my free pizzas, it's going to be a memory address. Then if I was to use the dereference operator, that would give me the first element within that array, pizza 1. So those are pointers. It's a variable that stores a memory address of another variable. Sometimes it's easier to work with an address. Instead of carrying 5 free pizzas with me and going house to house giving it away, I'll just tell people where the free pizza is. So those are pointers. Your assignment is to post a pointer in the comment section down below. And well, yeah, that's an introduction to pointers in C++. Hey, what's up everybody? So let's talk about null pointers, but first we'll need to know what a null value is. A null value is a special value that means that something has no value. When a pointer is holding a null value, that means that pointer is not pointing to anything. That's what we would call a null pointer. There is a keyword that represents that, null PTR. PTR meaning pointer. It's a keyword that represents a null pointer literal. One of the reasons that we use null pointers is that they're helpful when determining if an address was successfully assigned to a pointer. If we create a pointer, but don't assign it a value, we don't know where it's pointing to. It would be good practice that that pointer doesn't point anywhere. So let's create a null pointer. I'll create a pointer of the int data type. We use the dereference operator. Pointer. If I'm not going to assign this pointer an address right away, it would be good practice to assign this pointer null PTR, null pointer. Later on in your program, if you need to assign an address, let's say int x equals 123, I would just take my pointer, set this equal to the address of my variable. If you dereference a null pointer, it can lead to undefined behavior. Or if you dereference a pointer that's not assigned a value, well, that can lead to undefined behavior too. What some programmers do is that they'll check to see if their pointer is a null pointer before continuing, kind of like a system of checks and balances. We assigned our pointer the address of x. I would like to check to see if my pointer contains a valid address before dereferencing it. So we could say pointer equals null pointer. Was my pointer assigned an address, or is it still a null pointer? If my pointer is still a null pointer, that means we did not successfully assign an address to my pointer. There may be situations, such as when working with dynamic memory, where you attempt to assign an address to your pointer and it fails. This would be a good way to check to see if that failed or not, if your pointer still remains a null pointer. So let's say address was not assigned. Else, standard output, address was assigned. So let's run this. Currently our pointer is pointing to the address of x. Address was assigned. Now if for some reason we did not assign an address, I'll turn this line into a comment to represent that, well, our pointer is still going to be a null pointer. Address was not assigned. If your pointer is still a null pointer, it's not safe to dereference that pointer. If I need access to the value that's at that pointer, it would be safe to do so within this else statement. Standard output, dereference operator, pointer. So my pointer contains the number 123. If I were to dereference this null pointer, that would lead to undefined behavior. I have no idea what's going to happen. Don't try this at home, kids.
What the fuck?
A null pointer is a keyword that represents a null pointer literal. When declaring a pointer, it's good practice that our pointer is pointing to a valid address or this null pointer keyword, because otherwise we don't know where it's pointing originally. They're helpful when determining if an address was successfully assigned to a pointer. When using pointers, be careful that your code isn't dereferencing a null pointer or pointing to any free memory that we're not using, because that can lead to undefined behavior. So yeah, everybody, those are null pointers in C++. Hey guys, in this topic we're going to create a game of tic-tac-toe. We'll be working with random numbers. You may or may not need to include this header file. Include C time. We'll add some function declarations, then some definitions. Void draw board. There will be one parameter. A pointer to an array named spaces. Spaces will be a one-dimensional array that will keep track of all the markers, like what spots are taken, what spots are occupied. Player move. The parameters will be a pointer to spaces and char player. Computer move. A pointer to spaces, char computer. Check winner. A pointer to spaces, char player, and char computer. Then lastly, check tie. And all we need is a pointer to our array spaces. Oh, check winner and check tie will both return a Boolean value. Okay, let's add some function declarations. So after the main function, let's paste these. We do need to return some value for check winner and check tie because there is a return type. Just for now, as a placeholder, I'm going to return 0. But we'll change that later. Let's head to the main function and declare everything that we'll need. A character array named spaces. The size will be 9 spaces. We'll have 9 elements. Each contains an empty space. One, two, three, four, five, six, 7, 8, 9. Good. Char player. Pick a character that you'd like to be. You could do X or something else. Char computer. Pick a character for the computer. Let's begin with O. Boolean running, I'll set this equal to true. When we begin our game, we will immediately invoke the drawBoard function, then pass in our array. So remember, when we pass an array to a function, it decays into a pointer. So we don't need to create a pointer for this array. Within the drawBoard function, we will display a grid. So let's write something like this. Standard output, I'll add 5 spaces, 1, 2, 3, 4, 5, then a vertical bar, 5 spaces again, 1, 2, 3, 4, 5, vertical bar, 1, 2, 3, 4, 5, then a new line. Okay, let's copy this line. Right in the middle, I'm going to add one of the elements of our array, spaces. So right about there. Spaces at index 0. I'm going to copy this section of code. Right in the middle between the 2 vertical bars, I'll paste what we copied. Spaces at index 1. Then again, right in the middle, paste what you have. Spaces at index 2. This time we'll create a horizontal bar. Let's copy this. We'll replace the spaces with underscores. So right about there. Okay, let's see what we have. Okay, yeah, something like this. We'll have a player or the computer right in the center. So let's copy this line on top, paste it underneath, copy this line that displays elements of our array, paste it underneath, but change the element numbers 3, 4, 5. Then we'll copy this line, paste it underneath. Let's double check to see what we have. Okay, we're getting somewhere. Let's copy this line, paste it. Copy one of these lines where we display the elements of the array. Paste it underneath. So we are missing elements 6, 7, 8. Let's copy one of these empty lines. Paste it underneath. Then before and after we display this grid, I'll just display a new line. Standard output new line. And let's do that after. Okay, let's see what we have. Yeah, not too bad. There's our grid of 9 spaces. Okay, that is the drawBoard function. We can close out of this. We're done with it. When we invoke the drawBoard function, we will pass in our array, which decays to a pointer, and then prints our board. Let's add a while loop after the drawBoard function. While our condition is running. Running is set to true initially. When we exit out of the game, we'll set running to be false. The first thing that we'll do is invoke the player move function. Player move, but we need to pass in our array, spaces, as well as a player. Player. Then let's fill in the player move function. Okay, player move. I'll create a local variable named number. The user will enter in a number between 1 and 9, depending on what space they'd like to occupy with their marker. I'll create a do while loop. Do while. The condition will be not number is greater than 0, or not number is less than 8. The user can only enter in a number between 0 and 8. Those numbers correspond to the elements of our array, elements with indices 0 through 8. Within the do while loop, we'll ask for some user input, standard output, enter a spot to place a marker, 1 through 9. Whatever the user types in, we'll just subtract 1. Because the user doesn't know that arrays start with 0, supposedly. Standard input, number. So the user will enter in a number between 1 and 9. Then we will decrement the number by 1, because the array starts with 0. if spaces at index of number, whatever the user types in, is equal to an empty space. If that space isn't occupied, we'll add that marker to that spot. Spaces at index of number equals the player's marker. Then we'd like to break out of this while loop. So after the player moves, let's draw the board again to reflect any changes. Okay, enter a spot to place a marker. How about 1? Yeah, and there's our marker. Let's try it again. How about 9? Yep, and we are in the last spot, the bottom right corner. Let's enter in a number that's outside of this range, like 100. Enter a spot to place a marker. -1. Okay, so we're limited to the numbers 1 through 9. Even if I were to type 0, we still can't. So let's try something in the middle. That would be 1, 2, 3, 4, 5. Yeah, and there's our marker. I'm just going to add a colon, then a space. Okay, and that is the player move function. We can close out of this function. Let's work on the computer move function next. Within the while loop, let's invoke that function, pass in our spaces array, as well as whatever character the computer is. Then we will draw the board again right after. Just to update it. Within the computer move function, we'll create a local variable named number. We'll need a seed to generate a random number, srand. Within the parentheses, invoke the time function, pass in 0 or null, and we should be able to generate some random numbers. So I'm going to create a while loop. While the condition will be true, I would like to generate a random number between 0 through 8. We'll take number, set this equal to rand function, modulus 9. Number will be random between 0 and 8 technically. If we pick a spot number that is occupied already, we'll need to re-roll a random number. If spaces at index of number is equal to an empty space, we'll take spaces at index of number, set this equal to the computer's marker, then break out of this while loop. Let's test this function. After we pick a spot, the computer will pick a spot too. Yep, so the computer picked a spot right in the middle. Let's try it one more time. I'll pick the spot in the middle again, so that would be 5. And our computer picked spot number 2. Cool. Let's close out of the computer move function. After the player moves, then we draw the board again. We will check a winner. I'll use an if statement. Within the condition of the if statement, we will invoke the check winner function. The check winner function returns a Boolean value, so that's why we're placing it within the if statement. But we need to pass in a couple arguments, our spaces, the player, and the computer. If there's a winner, if this evaluates to be true, we will set running equal to false, and we will break. Let's add this if statement to after the computer moves too. Okay, let's fill in the check winner function. So right down here. We'll need to check all of the different win conditions. There's several. Normally I would use a switch, but it's going to get very complicated, especially for beginners. I think just to make this easier, we'll use a bunch of if and else if statements. Within the first condition of the if statement, we'll check to see if the first row all has matching characters. So we can do that by saying spaces at index of 0 is equal to spaces at index of 1 and spaces at index of 1 is equal to spaces at index of 2. If all 3 characters in the first row are the same, that means that somebody won. I'm going to use the ternary operator here. We have to determine who won, the player or the computer. Let's check to see if the first index, spaces at index 0, is equal to the player's marker. Ternary operator, like we're asking a question. If the player occupies the first row, then we'll print standard output you win. Otherwise, standard output you lose. Then I'm just going to add a new line here and here. Okay, there's one more thing we have to do with this condition, and I'll explain that. So let's run this. I'll pick spot number 9. You lose. The reason that we lost is that we're checking to see if the first row all has the same characters. They're technically all empty spaces, so our program thinks that somebody won because all of these characters match. There are 3 empty spaces. I'm going to amend this if statement. We'll want to ensure that none of the spaces are empty. And really, we only need to check the first space. I'll make this amendment. Spaces at index of 0 does not equal an empty space. And all these other conditions. If you'd like to keep this more organized, you can always surround some of these conditions with parentheses. I think it's more legible that way. Let's try that again, just to be sure that it's working. I'll pick something in the middle. Okay, yeah, so the computer doesn't win automatically if there's 3 empty spaces in the first row. Okay, so that is the first win condition. Let's copy this condition. I'll add else if. Now we'll check the second row. If spaces at index 3 is not equal to an empty space, and spaces at index 3 is equal to spaces at index 4, and spaces at index 4 is equal to spaces at index 5. Then does spaces at index 3 equal to player? Okay, so that is row 2. Let's copy and paste that else if statement. Then we'll need to check the last row. Spaces at index 6. 6 is 6 equal to 7, and is 7 equal to 8. So these conditions will check all of the rows. Then we'll need columns. Let's copy one of these else if statements, paste it. So we have 0, 0 is 0 equal to 3, and is 3 equal to 6. Okay, now time for the second column. Spaces at index 1, 1 right here as well, is 1 equal to 4, and is 4 equal to 7. Copy this again, paste it. Then we have the third column. 2, 2 is 2 equal to 5, and is 5 equal to 8. Okay, now the diagonals. Spaces at 0, 0 is 0 equal to 4, and is 4 equal to 8. Then the last diagonal. Spaces at index 2, 2 is 2 equal to 4, and is 4 equal to 6. If there's no win conditions, we'll have an else statement. We will return false. Then all we have to do at the end of this function is to return true. Somebody won. Okay, so let's test this. I'll try and win with the first row. 1, 2, 3. You win. This time I'm going to try and lose. 1, 2, 4, 7. Whoops, 7's taken. 8. There we go, you lose. We can close out of the check winner function. We know that it's working. Then we just need to check to see if there's a tie, if there's no more spaces available. Within the main function, after our if statements, we'll add else if. We'll invoke the check tie function, pass in our spaces. Check tie returns a Boolean value. If it's true, we will set running to be false, then break. Then add that after the computer move section too, so right here. Then let's fill in this function. Within the check tie function, we'll iterate over the elements of our array spaces. We'll use a for loop. For int I equals 0. We'll continue this as long as I is less than 9 because there's a total size of 9 spaces. increment I by 1 if spaces at index of I is equal to an empty space. That means we can continue. Return false. There's still empty spaces. If we iterate over our array and there's no empty spaces, well then we'll display standard output, it's a tie. I'll add a new line. Then we will return true. And we can get rid of that. Okay, so let's close out of this check tie function. Then after we exit our game, outside of this while loop, let's display a message. Standard output, thanks for playing. Alright, and that's everything. Let's run this. I'm gonna try and get a tie this time. 1, 2, 6, 7, 8. It's a tie. Thanks for playing. Alright everybody, that is a game of tic-tac-toe for beginners. If you would like a copy of this code, I'll post this in the comments section down below. And well, yeah, that's a game of tic-tac-toe using C++. Hey everybody, we finally made it to dynamic memory. Dynamic memory is memory that is allocated after the program is already compiled and running. To allocate dynamic memory, we use this new keyword. It's an operator. It allows us to allocate memory in the heap rather than the stack. It's useful when we don't know how much memory we'll need. It makes our programs more flexible, especially when accepting user input, because we have no idea what the user is going to type in. Here's an example. We'll start with a basic integer variable, but we'll allocate memory in the heap rather than the stack by using that new keyword. I'll create a pointer. Int dereference operator p num. Now it's good practice when you declare a pointer, but don't assign it right away, to give it a value of null, meaning no value. To allocate memory in the heap rather than the stack, I'll take my pointer, set this equal to, use the new operator, then a data type. I'll use up enough space in the heap for one integer. The new operator will return an address. We're storing that address within pnum because it's a pointer. It's pointing to a memory location where we're going to store an integer. Later on in your program, whenever you would like to store a value, we can use the dereference operator, our pointer, then assign some value. Like 21, I don't know. Just for fun, I'm going to display the address that's stored within the pointer. Address pnum, then I'll add a new line, as well as the value. Value, dereference operator, pnum. Our pointer is storing this address, and at this address in the heap, that address contains this value, 21. Now it's very good practice, if not expected, whenever you use the new operator, you'll also want to use the delete operator when you're no longer using that memory space. So at the end of this program, or earlier if you choose, we will delete our pointer. Delete pnum. We're freeing up the memory at this address. If you don't, you may cause a memory leak, and it's best to avoid that. Whenever you use the new operator, you probably should be using the delete operator someplace within your program. Here's another example. We're going to dynamically create an array. Let's create an array of grades. Char, then we'll need a pointer, dereference operator, p grades. Set this equal to null if we're not going to assign this pointer right away. Then to dynamically create an array, we will take our pointer, set this equal to new, the data type, char. If this is an array, we add a set of straight brackets. Within the straight brackets, we will list a size. If I have 5 grades to enter in, I would type in 5. But if we already know the size of the array before we even run the program, we might as well do that normally, like create a normal array. There's no point to allocating memory dynamically. We would want to do that when we don't know what the size is going to be. So I propose we ask for some user input. Let's say int size. We'll create a prompt. Standard output. How many grades to enter in? Standard input size. will dynamically allocate enough memory in the heap depending on how many grades the user has to enter in. I'll just create a for loop so that we will ask the user to enter in some grades. Int I equals 0. I will continue this as long as I is less than size. Increment I by 1. Standard output. Enter grade number I plus 1 because I will be 0 to begin with. And I'm just going to add colon space afterwards. Standard input p grades. That's our pointer. Now we can either add plus I or use those straight brackets at index of I. Either way. Let's display all of the grades. Int I equals 0. I is less than size. I plus plus. Standard output p grades at index of I. I'll separate each with a space. And remember, if we no longer need this array, we should delete it to prevent a memory leak. If we have to delete an array, we'll add a set of straight brackets after delete, then our pointer. P grades. And let's try it. How many grades to enter in? So we don't know what the user is going to type. Let's say 6 grades. Enter grade 1, A, B, C, D, F, A. And here are the grades. So that's why dynamic memory is useful. It's memory that is allocated after the program is already compiled and running. We use the new operator to allocate memory in the heap rather than the stack. It's useful when we don't know how much memory we will need. It makes our programs more flexible, especially when accepting user input. So that is an introduction to dynamic memory. We'll have more practice with this in the future, so don't worry. If you would like a copy of the code that we worked on, I'll post that in the comments section down below. And well, yeah, that's an introduction to dynamic memory in C++. Hey guys, I gotta explain recursion. Recursion is a programming technique where a function invokes itself from within. We break a complex concept into repeatable single steps. Many problems we can approach iteratively or recursively. Some of the advantages of recursion include less code to write, and typically it's cleaner. It's also useful for sorting and searching algorithms. However, some of the disadvantages of recursion is that it uses more memory and is slower. There's a trade-off. It's up to you if you'd rather use an iterative approach or a recursive approach. Here's an example. We'll break a complex concept, maybe such as walking, into repeatable single steps. To accomplish the task of walking, we would take a single step and then just repeat that a bunch of times. We'll do this first iteratively, then recursively. So let's create a function to walk. Void walk. There will be one parameter, a number of steps. Let's define this walk function. We'll use an iterative approach first. To do that, we can use a for loop. We'll set int I equals 0. We'll continue this as long as I is less than our steps. Then increment I by 1. I will display just you take a step. Then I'll add a new line. So we will invoke this function, pass in how many steps we would like to walk. I would like to walk 100 steps. And here we go. We printed, you take a step 100 times. This is an iterative approach. If we were to take a recursive approach, we would invoke this function from within itself. So I'm going to turn this for loop into an if statement. We'll need a base case. When do we stop? If steps is greater than 0, we will display you take a step. Then I'm going to invoke the walk function from within itself. Then I will pass in steps minus 1. This would be a recursive approach. We're invoking the walk function from within itself. You'll end up in a function, within a function, within a function, within a function, so on and so forth. So when I run this would do the same thing, but we've done so recursively. The advantages with recursion is that the code tends to be easier to write. I find this if statement a lot easier to understand than that for loop. although they're both pretty simple. However, with recursion, it uses more memory and it takes more processing time. In the case with our walk function, I would probably stick with an iterative approach. There's really not much benefit in this case. But in the case of, let's say, a searching algorithm or navigating a tree data structure, recursion would really help us with that. So let's say we don't have a base case. That's when we stop. What if I just call the walk function forever? Well, we end up in an infinite loop, and we would encounter what's called a stack overflow. When you invoke a function, you add what's called a frame to the stack. When your stack is overloaded, you'll encounter a stack overflow. So that's one problem with recursion. So let's try a different example. We'll create a factorial function. If you don't remember, factorial is a mathematics concept where you take a number and you multiply that number times the previous number minus 1 times the previous number minus 1 times the previous number minus 1 until you reach 1. You multiply all these numbers and you're given a result. I'm going to demonstrate a function to do that both iteratively then recursively. Let's begin with an iterative approach. We will return an integer. This function will be named factorial. We'll pass in an integer named num. I'll immediately display the output, standard output, factorial, then pass in some number, maybe 10. Let's define this function. If I was to take an iterative approach, I would write something like this. Int result, this will be a local variable. I'll set this equal to 1. I'll create a for loop. Int I equals 1. We'll continue this as long as I is less than or equal to our number. Increment I by 1. I will take our result equals result times whatever I currently is. At the end of this program, we will return result. Factorial 10, that would be 3,628,800. If I was taking a recursive approach, I would write something like this. We would need a base case. When do we stop? If num is greater than 1, we will return num times, invoke factorial again, our number minus 1. Else, we will simply return 1. This would do the same thing, but recursively. Factorial 10 is 3,628,800. Those were two different approaches to the same problem. When we did this recursively, we have a function call inside of a function call, inside of a function call, inside of a function call. You get the idea. Personally, I find a recursive approach to be a lot easier to read and understand. Although remember, it uses more memory and is slower. When you start to learn about sorting algorithms, that's when recursion is really going to help you quite a lot. It will simplify the steps. So that's recursion, everybody. It's a programming technique where a function invokes itself from within. We break a complex concept into repeatable single steps. Whenever you see a function invoking itself from within, you'll know that that's recursion. Hey, if you would like a copy of this code, I'll post this in the comment section down below. And well, yeah, that's recursion in C++. Hey everyone, let's discuss function templates. A function template describes what a function looks like. They can be used to generate as many overloaded functions as needed, each using different data types. How is this useful? Suppose we have a max function that will accept and return an integer. Int max, the parameters will be int x, int y, will return, I'll use the ternary operator here, is x greater than y? If so, return x. If not, return y. This function is compatible with integers as arguments. Let's display standard output max, then pass in two integers like 1 and 2. So this would return the number 2. But what if I would like to use this function with doubles, such as 1.1 and 2.1? Well, we're truncating that decimal portion. We're returning 2, not 2.1. If I want this function to be compatible with doubles, normally I would have to create an overloaded function that accepts doubles and returns a double. replace int with double. And I guess this would work technically. The value returned is 2.1. What about characters? How about the character 1 and the character 2? Technically, we could use the max version that accepts integers because there's an associated ASCII value with each of these characters. But I would like an overloaded function that accepts and returns characters. Char, char, char. So this would return the character 2. This is a lot of work creating 3 overloaded functions that each do the same thing. The only difference is that they accept and return different data types. What if we could write one function that will accept any data type? Well, that's what function templates are. To create a function template, take your function, replace any data type with t. We're returning an integer, let's instead return t. The data type of x will be t, same thing with y. Using t as a common naming convention, I like to think of it as thing. Like, we're not sure what the data type is, we're returning a thing. That's just how I think of it. However, our compiler doesn't know what t is exactly. We'll need to add a template parameter declaration. Before this function template definition, we'll add a declaration of what t is. So type template, angle brackets, type name, t. And that's it. This function template will work with many data types. Characters, doubles, integers, you name it. So yeah, just replace the data type with t. Then be sure to add a template parameter declaration. Now here's a scenario. What if you need to mix and match the data types? I'll find what the max is between the integer 1 and the double 2.1. Well, we have a problem. No matching function for call toMax int double. With this function template, it's only set up to receive arguments of the same data type. Now we're passing in 2 different data types. What we could do within our template parameter declaration is add another template name. I'm going to add type name u because u comes after t in the alphabet. Then if you needed more, you could add v, w, x, so on and so forth. I'll change one of these t's to a u. This function template is set up to receive up to 2 different data types as arguments. But there's one more change we need to make. So we don't have that error anymore, but the decimal portion of our double is truncated, it's returning 2. That's because we're still returning t, and t we set to be an integer in this case. Do we set the return type to be t or u? Actually, better yet, we can set this to auto. Using the auto keyword, the compiler will deduce what the return type should be. This should return 2.1. Alright everybody, that is a function template. It describes what a function looks like. They can be used to generate as many overloaded functions as needed, each using different data types. I like to think of it like a cookie cutter. We're determining what the shape is, but the arguments, the dough that we use for our cookies, can be different. But the cookies will end up having the same shape. One of the main benefits of using function templates is that we only have to write a function once, and then it's compatible with different data types. So you don't need multiple versions of the same function. We'll generate functions using this template as needed. So yeah, those are function templates, everybody. Your assignment, if you choose to do so, is to write a function template in the comments section down below. And well, yeah, those are function templates in C++. Well, okay then everybody, we gotta talk about structs. A struct is a structure that groups related variables under one name. Think of an array. An array can store multiple values of the same data type. Well, a struct can store multiple values of different data types. We can store strings along with ints, doubles, booleans, etc. To create a struct, let's do so outside of the main function. Type struct. Then we need an identifier. This is kind of like the data type. Suppose we're going to group related variables for students. I'll name this identifier student. Within the structure of student, variables that we declare are known as members. I think each student should have a name member. This will be of the string data type, string name. I'll declare this but not yet assign it, as well as a GPA. That could be of the double data type. Then a Boolean variable if they're currently enrolled or not. Enrolled. Then be sure to end your struct with a semicolon. Our struct student is kind of like its own data type. We can use this data type to declare variables. I'll create a student variable of this data type, and that variable will have these three different members: a name, a GPA, and a Boolean variable for being enrolled. Much like with creating a variable, we type the data type, student, and then some name, some identifier. Let's name the first student student1. Student1 will have its own name, GPA, and enrolled status. If I would like to assign the name member of student1, I would type the name of the student, student1, followed by dot. Members can be accessed with a dot, also known as the class member access operator. I'll assign the name member and set this equal to SpongeBob. I'll assign student1's GPA, student1.gpa. I'll give SpongeBob a solid 3.2. Then I could set his enrolled status. Student1.enrolled. I'll set this to be true. Then we could access these members. I'll display them. Standard output student1.name. I'll add a new line. Let's do the same thing with GPA and enrolled. Student1.gpa, student1.enrolled. This is what this looks like. We have a student variable. The name member is SpongeBob. SpongeBob has a GPA of 3.2. When accessing Boolean variables, 1 corresponds with true, 0 corresponds with false. Enrolled is set to true, so that would return 1. Let's reuse the struct to create a second student. I'll just copy what we have here, then paste it. We'll give the second student a different identifier, such as student2. Student2 will have a name member of Patrick, a GPA of 2.1, and he will be enrolled. That's set to true. Let's display student2's members. Student2.name, student2.gpa, then student2.enrolled. These first members correspond with student1, SpongeBob 3.2, 1 for true. The second set is for student2. Patrick has a GPA of 2.1, and Patrick is currently enrolled. Okay, one last example. Let's create student3. Let's copy what we have, paste it. Student, student3, student3.name, student3.gpa, student3.enrolled. Student3's name will be Squidward. Squidward has a GPA of 1.5. Let's set enrolled to be false. Then display student3's members. Student3.name, student3.gpa, student3.enrolled. And here are student3's members. Squidward, 1.5, and 0, that means false. Now with members, you can set a default value. I'll set enrolled to be true. Then we don't need to explicitly state that. Underneath SpongeBob, Patrick, and Squidward, their enrolled member is all set to 1. With members, you can set a default value. So yeah, those are structs. It's a structure that groups related variables under one name. Structs can contain many different data types. Variables in a struct are known as members, and members can be accessed with a dot, the class member access operator. So those are structs. Your assignment is to post a struct in the comments section down below. And well, yeah, those are structs in C++. Hey everybody, in this topic I'm going to show you how we can pass a struct to a function in C++. Suppose we have a struct. The identifier of the struct will be cars. Then we'll create some members related to cars. How about a model, standard string model, a year, int year, then a color, standard string color. Then let's go ahead and create two car structs. How about car, car1, car2. Then we'll assign the members. car1.model, pick a model of a car that you like. Then a year. And a color. Let's do the same thing with car2. Car2.model, card2.year, card2.color. Let's pick some different data. That'll work. Suppose we have a function to display the members of a car. Void. How about print car? We're printing the members. We'll need some parameters. The data type of what we're passing in are car structs. So we'll list that as the data type. Then some nickname for the argument that we receive. How about just car? Then I will display the members. Standard output car dot model. Should probably add a new line too. Then do the same thing with year and color. Car.year, car.color. Let's test this by printing car1. Print car1. We will pass the name of a struct as an argument. Then I think we're just missing a function declaration, so if you're missing that, be sure to add that. There. Now let's run this. Okay, here's our car. Mustang 2023, and the color's red. Now with structs, they're passed by value rather than passed by reference. If we pass a struct as an argument, what we're doing is creating a copy of the original struct. To demonstrate that, let's display the address of car1 before and within the function. Standard output address of operator car1. I'll add a new line. Then let's do that within the function too. The parameter name is car, not car1. There. So let's try that. So these addresses are different. When we pass the struct to a function, the function will create a copy of it. It's passed by value. We're displaying the members of the copy rather than the original. If you need to work with the original struct, you can use the address of operator. We're passing a reference to the original car struct. Then be sure to change that within the function declaration as well. So let's take a look at the addresses now. Yeah, these addresses are the same. Car2 is feeling pretty lonely, so let's print car2 as well. Print car, pass in car2 as an argument to this function. So we should have car1 and car2. This time, let's change one of the members within a function. Let's create a function to paint car. Paint it a different color. Paint car. There will be two arguments. An address to a car, as well as a color, which will be of the string data type. Be sure to add a function declaration if you're missing it. Then within this function, we will take our car.color equals the new color that we receive. Now, before we print our cars, let's paint them a different color. Paint car. We have two arguments this time, a car struct and a new color. Let's paint our Mustang silver. Then let's paint car2 maybe gold. Then let's display this. Okay, our Mustang is now silver and our Corvette is now gold. So if we didn't use the address of operator when painting our car, let me show you what happens. Our cars are still the original colors, red and blue. What we did within this function is that we created a copy of our car structs and changed the color of the copies rather than the originals. So if you need to make any changes to the original, you would want to use the address of operator. So that's how to pass structs to functions. You can pass by value, which can be expensive, or you can pass by reference. Your assignment, if you choose to do so, is to post a function that accepts a struct as an argument. And that's how to pass structs to functions in C++. Hey everybody, we gotta talk about enums. Enums also means enumerations. It's a user-defined data type that consists of paired named integer constants. They're great if you have a set of potential options. Here's an example. Suppose we have a day of the week. Standard, string, today. Then pick a day. I'll pick Sunday. Normally you can't use strings within switches, but we can use enums, which are kind of similar. Let me explain. So I'm going to create a switch. We will examine today. Normally we can't do this because it's a string. We'll examine today against many matching cases. Case, Sunday, and I'll speed up the footage. Okay, here's my switch. Depending on what day of the week it is, we'll display a custom message. It is either Sunday through Saturday, one of these days. So normally we can't use strings within switches. This is what happens when we attempt that. Error, switch quantity, not an integer. Something similar that we can use are enums. They're paired named integer constants. We have a name and an associated value. They're interchangeable. At the top of my program, I will declare enum, then a name for this set of enumerations. Let's say day, for day of the week. We have Sunday, Monday, Tuesday, and you know the rest. You can associate a value with each of these names. Sunday equals 0, Monday equals 1, then we'll just continue on with the rest of these. I'm going to group these together like that. Okay, we have our enum set up. This identifier is kind of like the new data type. We're not working with strings anymore, we're working with days. These are a set of potential options. Each option is a pair of a name and some associated value. You can really pick any value. I went with the numbers 0 through 6 to represent the day of the week. I'm going to set today to Sunday. This name. We can now use this within a switch. There's an associated integer value, but we'll change the cases from strings to that enum data type. And this would work. It is Sunday. Within the cases, you could use the associated values as well. I'm going to change today to be Friday. Case 0 is Sunday. Monday is 1, 2, 3, 4, 5, 6. It is Friday. So that also works, but I don't think it's as readable. Another cool thing with enums is that enum variables take only one value of this set. If I try and make up some value like pizza day, well, we can't do that. Pizza day was not declared in the scope. Here's a few other enum examples. You could create a set of enums for flavors: vanilla, chocolate, strawberry, mint. An important note is that if you're working with enums and you don't assign an integer value to each of these names, you'll implicitly assign 0 to the first name, then 1, 2, 3. Kind of like what I did up here, but we explicitly assigned those values. We have 6 colors, or maybe planets. I have a set of enums of the 9 planets in our solar system. The associated integer is the size of each planet in kilometers. So yeah, those are enums. They're a user-defined data type that consists of paired named integer constants. They're great if you have a set of potential options. Your assignment is to post a set of enums in the comments section down below. And well, yeah, those are enums in C++. Hey everybody, so we have finally made it to object-oriented programming. An object, think of it as a collection of attributes and methods. Attributes are characteristics of an object. Methods are functions that an object can perform. Objects can be used to mimic real-world items. So look around you right now. Next to me I have a phone, a book, and a dog. Think of attributes as characteristics. What kinds of characteristics would a phone have? Maybe a version number, a charge, a service provider. Objects can also contain methods. What kinds of actions can a phone perform? They can make calls, receive calls, play games. Now with a book, some of the attributes of a book could be maybe an author, number of pages. Let's see, what kinds of methods can a book perform? Really not much. You can open a book and you can close it, so those are just a few. Okay, lastly, how about a dog object? Some of the attributes of a dog could be a name, an age, maybe a breed of dog. Then what kinds of actions can dogs perform? They can eat, they can bark, they can sleep, maybe play fetch. So I think you get the idea. An object is a collection of attributes and methods. Now, to create an object, we can use a class. A class acts as a blueprint to create objects. Let's create a class to create human objects. I will type class human, curly braces. I'm going to add a public access modifier. We'll learn about access modifiers pretty soon. I would like these attributes and methods to be publicly accessible. Let's start with the attributes of humans. What kinds of characteristics can humans have? How about a name? This will be of the string data type. I'll declare this attribute, but not yet assign it. Maybe an occupation, like a job. Standard string occupation. Then maybe an age. Int age. Our class human has these attributes. Humans have a name, an occupation, and an age. That's good enough for this example. Now let's cover methods. A method is a function that belongs to a class. It's something that an object can do, an action it can perform. What sorts of actions should our humans be able to perform? How about an eat method? Void eat. I'll just display a message, standard output. Let's say this person is eating. Humans can drink. Void drink. Standard output. This person is drinking. Okay, one last example. How about sleep? Humans sleep, right? Void sleep. Standard output. This person is sleeping. Good enough. Oh, then make sure we add a semicolon to the end of the class. Perfect. Okay, so we now have a human class. We can use this class as a blueprint to create human objects. Each human object will have a name, an occupation, and an age. They can also eat, drink, or sleep. They have their own functions, which we call methods. So to create a human object, we will type the name of the class, human, then a unique identifier. How about human1? That's creative. So human1 is an object. Human1 has a name, an occupation, and an age, but we have not assigned these attributes. Let's say human1's name, human1, member access modifier, which is a dot, name equals Rick. Then human1's occupation equals scientist. Human1's age equals 70. Let's verify that this worked by printing out these attributes. Standard output human1 dot name. I'll add a new line. Then let's repeat this for occupation and age. Human1 dot occupation, human1 dot age. Human1's name is Rick, his occupation is a scientist, his age is 70 years old. So this part is kind of similar to structs. However, objects can also perform actions. They have methods. Rick can eat, drink, and sleep. So to invoke those methods, I would type the name of my object, human1, and let's have human1 eat. So human1 dot eat, add a set of parentheses to invoke this method. Okay, this person is eating. Let's also test drink and sleep. Human1 dot drink, human1 dot sleep. Okay, this person is eating, this person is drinking, this person is sleeping. And that is our human, human1. For more practice, let's create a second human. Human2. I'm going to copy these lines. Let's change human1 to human2. Human2's name will be Morty. Occupation will be student. Age, what about 15? I'm going to display the attributes of human2 this time. Then I'll have human2 invoke its methods. Eat, drink, then sleep. Okay, human2's name is Morty. Their occupation is a student. Morty is 15 years old. Then Morty can perform these actions: eat, drink, and sleep. Now you can assign some default attributes. So let's say that all humans we create will be named Rick. It's kind of like we're cloning him. His occupation will be scientist. Age will be 70. I'm not going to assign these attributes. What I did is that I added some default attributes. So we have human1 and human2. I'll display the attributes of human1 first, then human2. Human1.name, occupation, age. Then we have human2's attributes as well. So remember, I am not assigning these attributes within the main function. We have two humans, they're both named Rick, they're both scientists, and they're both age 70. Okay, now here's one last example to really get the hang of objects. Let's create a different class this time. How about cars? Class, car. Let's add a public access modifier. Then what kinds of attributes would cars have? Perhaps a make, standard string make, a model, standard string model, a year, that would be an int, then maybe a color, standard string color. You can add some default attributes, but I'll just leave those empty for now. You can add some methods. What kinds of actions can cars take? I guess you can accelerate. Void accelerate. Standard output. What can we print? You step on the gas. Then maybe brake. Void brake. Standard output. You step on the brakes. Then be sure to add a semicolon to the end of your class because I always forget to do that. Okay, we now have a car class. It acts as a blueprint to create car objects. To create an object, we would type the name of the class, car in this example, then a unique identifier for the object. Let's say car1. Then we can assign some of the attributes of this car object. Car1 dot make, maybe Ford. Car1 dot model equals Mustang. I like Mustangs. Car1 dot year equals 2023. Then a color, car1 dot color, maybe silver. Okay, then just to test these, let's print these attributes. Standard output, car1 dot make. I'll add a new line. Let's copy this line, paste it 3 times. Then we'll display the model, year, then color. Okay, our car object is a Ford Mustang. The year is 2023. The color is silver. Not only does our car have attributes, but it has methods, actions it can perform as well. Our car can accelerate and it can brake. Let's test that. Car1 dot accelerate. Car1 dot brake. Okay, you step on the gas, you step on the brakes. Then if I need a second car object, I can type car, car2. Then I can assign the attributes, and I have access to its methods. So yeah, that's an object, everybody. It's a collection of attributes and methods. Attributes are characteristics of an object. Methods are functions that an object can perform. So yeah, those are objects, everybody. In the next video, we're going to cover constructors. Your assignment is to post a class in the comment section down below. So yeah, that's an introduction to object-oriented programming in C++. Hey everybody, welcome back. So in today's video, we're going to discuss constructors. A constructor is a special method within a class that is automatically called when an object is instantiated. It's useful for assigning values to attributes as arguments. Before, when we were assigning attributes to an object, we would say, for example, car1.make equals Ford. Well, with a constructor, we can do that automatically. Here's an example. This time, let's create a student class. Class student. I'll add a public access modifier. What attributes should students have? How about a name? Standard string name. Int age, double GPA. Sounds good to me. Then if I need to create a student object, I would type the name of the class, student, a unique identifier for this specific object, let's say student1. Then to assign some of the attributes right away, I could use a constructor. We do have a constructor that is automatically called behind the scenes, but we could explicitly set one up. The constructor has the same name as the class. In this case, student, add a set of parentheses, add a set of curly braces. Think of this as a function. We can set up parameters. When we instantiate a student object, we will automatically call this function, the constructor, then pass arguments. Let's set up some parameters. We have standard string name, int age, double GPA. Then when I instantiate a student object, I will add a set of parentheses after the object name, then pass in my arguments. Let me just zoom in real quick. Okay, in order to instantiate a student object, we need to pass in a name, an age, and a GPA. So for the first student, student 1's name will be SpongeBob. His age will be, I don't know how old SpongeBob is. Let's say he's 25. SpongeBob's GPA will be a solid 3.2. When we instantiate our student object, we will pass these values as arguments to the constructor. Now, to assign these attributes with these parameters, we first need to select these attributes. In this example, I gave them the same name, just to remove ambiguity. If I'm referring to these attributes, I will type this, then an arrow, name equals the name of the parameter, name. This name equals my name parameter. This arrow age equals my age parameter. This arrow GPA equals my GPA. So now let's test this. I will display student 1's name, age, and GPA. Standard output, student1 dot name, add a new line. Then we have age, then GPA. Okay, we got SpongeBob, he's 25 years old. His GPA is 3.2. So you can see that we don't need to necessarily add these values to these attributes manually. You can do that automatically with a constructor. So another way in which you may see this constructor set up is with the parameter names being different from the attribute names. Perhaps instead of name, age, and GPA, let's say X, Y, then Z. If the attribute names are different from the parameter names, you don't need this keyword. You could say name equals X, age equals Y, GPA equals Z. And this would work too. If you prefer this way of doing things, you can do that. Just my own personal preference, I like to use this keyword and then keep my parameters the same. But that's just me. You do you. Let's create a couple more students. And it's kind of nice because we can reuse this constructor. Let's create student 2. Student, student 2. Student 2 will be Patrick. I don't know how old Patrick is. Let's say Patrick is 40. Patrick's GPA will be 1.5. Okay, to test this, let's display student 2's name, age, and GPA. Okay, we got Patrick. He's 40 years old. GPA is 1.5. One last student. Student, student 3. Student 3 will be Sandy. Sandy is, how about 21 years old? And Sandy's GPA is a perfect 4.0. Okay, now we'll display student 3's name, age, GPA. Okay, we got Sandy. Her age is 21. GPA is 4.0. Let's do one last example just to reinforce our understanding of constructors. Let's create an entirely new class. Let's go back to our car class. I'm going to get rid of all of this. So we need a class car, set of curly braces, add a semicolon to the end. I will add a public access modifier. In the last topic, we decided that cars had 4 attributes: a make, standard string make, a model, standard string model, int year, standard string color. Now we'll create a constructor for our car objects. It has the same name as the class name, car, set of parentheses, set of curly braces. We can set up some parameters. We have make, model, year, and color. I think I'm just going to copy this to save time. You can rename these if you want, but I like to keep them the same. Then I will assign this arrow make equals make, this arrow model equals model, this arrow year equals year, this arrow color equals color. When we create a car object, we'll need to pass in these arguments. I will create car1, add a set of parentheses, pass in my arguments, a make, model, year, and color. I'll create a Chevy Corvette. The year will be 2022. The color is blue. I'm going to display the attributes. Standard output car1.make. I'll add a new line. Then I will display the model, year, then color. Model, year, color. Car1 is a Chevy Corvette. The year is 2022. The color is blue. Let's create a second car. Car2. Car2 will be a Ford Mustang. The year will be 2023. The color will be red. I will display Car2's attributes. We have a Ford Mustang. The year is 2023. The color is red. So yeah, that's a constructor, everybody. A constructor is a special method that is automatically called when an object is instantiated. It's useful for assigning values to attributes as arguments. When you create an object from a class, add a set of parentheses, then add your arguments. Within the constructor, you can assign those arguments to the attributes of that class. In the next topic, we'll cover overloaded constructors. If you're looking for some additional practice, in the comments section down below, post a class that contains a constructor. And well, yeah, those are constructors in C++. Overloaded constructors are when we have multiple constructors with the same name but different parameters. They allow for a varying number of arguments when instantiating an object. Here's an example. We'll create pizza objects from a pizza class. Let's type class, pizza, add a set of curly braces, a semicolon to the end. We'll make our members publicly accessible. So pizzas, they can have a variable number of toppings, right? You can have no toppings, 1 topping, 2 toppings, 3 toppings. Suppose we have just 1 topping to begin with. Topping 1. And that will be of the string data type. Standard string topping 1. Then I will create a pizza constructor. It has the same name as the class name, pizza, parentheses, curly braces. We'll set up some parameters. Standard string topping 1. In order to construct a pizza, we have to pass in 1 topping. So let's do that. We have pizza, pizza 1, and I will pass in 1 argument for a topping. I feel like pepperoni. Then we'll just need to assign this argument to this attribute. This arrow topping 1 equals topping1, the name of this parameter. Then to test this, let's display topping1. Standard output pizza1 dot topping1. Okay, we have pizza 1 that contains pepperoni. Now, what if you would like a pizza that has 2 toppings? Suppose we have pizza 2, pizza 2. This time, I'm going to attempt to pass in 2 arguments. How about mushrooms and peppers? Well, when I run this program, we're going to have an error. Error, no matching function for call to pizza with 2 arguments. We can create an additional constructor that accepts different arguments. Let's copy what we have and paste it. This constructor will take 2 string arguments, topping1 and topping2. So we have 2 toppings this time, and I should probably create another attribute for a second topping. Standard string topping2. This topping 2 equals topping 2. So now with pizza 2, let's display topping 1 as well as topping 2. Now pizza 2 contains mushrooms and peppers. What if you would like a pizza with no toppings, like a plain cheese pizza? Well, we could set that up. Pizza 3. I'm going to attempt to add a set of parentheses after pizza 3, but pass in no arguments. But we have a warning. Our compiler is saying we should get rid of the parentheses. If we're passing in no arguments, we don't need that set of parentheses. But we still have an error here. No matching function call for pizza with no arguments. If we're creating an object and passing in no arguments, we'll need a matching constructor. So at the top, I'll create a pizza constructor with no arguments. And that should make that error go away. So this should run and compile just fine then. Yep, no errors. So yeah, those are overloaded constructors. You can have multiple constructors with the same name as long as the parameters are different. We have 3 constructors with the same name. We can create a pizza with no toppings, 1 topping, or 2 toppings. Overloaded constructors allow for multiple objects with a varying number of attributes. If you're looking for some additional exercises, post a class with overloaded constructors in the comment section down below. And well, yeah, those are overloaded constructors in C++. Hey everyone, let's talk about getters and setters. Getters and setters are used within this concept of abstraction, where we hide any unnecessary data from outside of a class. Getters are functions that make a private attribute readable. Setters are functions that make a private attribute writable. Here's an example. I'm going to create a stove object. Class stove. Then I will instantiate a stove object. Stove. In previous topics, when we created attributes, we would use the public access specifier, then write any attributes. In this example, let's say int temperature. I'll go ahead and set this to 0 right away. Since this attribute temperature is public, it's accessible from outside of the class. That means that people can change it. For example, I will take my stove object, set the temperature attribute to a really high setting that doesn't exist, like 1,000,000.
This is fine.
Then I can display the temperature. Standard output, the temperature setting is stove.temperature. The temperature setting is 1,000,000. I don't want people to mess with my temperature attribute. What I could do instead is set these attributes to be private. We're following that rule of abstraction. We're hiding any unnecessary data from a user that they don't need. We no longer have access to this temperature attribute from outside of the class. You can see we have some red underlines. Temperature is private within this context. This is a hidden attribute from the outside world. If I need access to the value found within this temperature, I can write a getter. It's a function that will make an attribute readable. I'll add a public access specifier, then write a getter. We're returning an integer. I'll write get, then the attribute name. Temperature. All I'm going to do is return our temperature. I can no longer update or change the temperature. It's readable but not writable, so I'm going to turn this line into a comment. In place of accessing this attribute directly, I'm going to invoke the getTemperature method. Stove.getTemperature, add a set of parentheses. Now the current temperature setting is set to 0. Adding a getter will make an attribute readable. If you need a private attribute to also be writable, you can add a setter. Void set temperature. This arrow temperature equals our temperature that we pass in. Then we just need a parameter. Int temperature. In order for a user to change the temperature, they would need to invoke the setTemperature method. Then they can pass in a new temperature. Using this setter, they can still set the temperature to whatever they want, like 1,000,000 in the previous example. The temperature setting is set to 1,000,000. Within a setter, we can add some additional logic or checks. Before we do set the temperature, let's check to see what the temperature is. If the temperature the user passes in is less than 0, we will set this temperature to be 0. Else if the temperature is greater than or equal to 10, suppose this is a knob with different settings, the numbers 0 through 10. This temperature equals 10. In case they type in 1,000,000, it'll just max out at 10. Else, this temperature equals temperature. I could attempt to set the temperature to 1,000,000, but it would just max out at 10. Or we could try a negative number like -3. Well, now the temperature setting is set to 0, as if the stove was off. Or anything in between, maybe 5, something right in the middle. The temperature setting is 5. So yeah, that's kind of the purpose of getters and setters. They make a private attribute either readable or writable, or both if you use both. One additional step you can take too is that if you have a constructor, you can invoke the setters within a constructor. Within my stove class, I have a constructor. If we were to receive a temperature, we could set the temperature right away. So we already have this line of code within our setter, so we don't necessarily need this line again. We would instead invoke the setter. Set temperature, pass in our temperature. Then if I was to instantiate a stove object, I would have to pass in a temperature. I'll set it to be 0. And this temperature setting is set to 0. So yeah, those are getters and setters, everybody. A getter makes a private attribute readable. A setter makes a private attribute writable. Within the getters and setters, you can perform additional checks or logic, which is pretty nice. If you're looking for some additional practice, post a class that has a getter and setter in the comments section down below. And well, yeah, those are getters and setters in C++. Hey guys, let's talk about inheritance. Inheritance is when a class can receive attributes and methods from another class. The receiving class is known as a child class. The class that's being inherited from is known as the parent class. It's kind of like how children will inherit their parents' genes and some of their physical traits. It's kind of the same concept. A benefit of inheritance is that it helps to reuse similar code found within multiple classes. Here's an example. We will create an animal class. The animal class will be the parent class. Class animal. I'll make these members publicly accessible. all animals will have a Boolean attribute that we will name alive. If you're an animal, you're alive. Then let's add a method. Maybe an eat method. All animals should be able to eat. Void eat. We'll just print a generic message. Standard output. This animal is eating. I'm going to create two classes, a dog class and a cat class. They will inherit from the animal class. Let's begin with dog. Class dog. To inherit from another class, you would add a colon, then public, the name of the parent class. Dog will inherit from the animal class. Then a set of curly braces, semicolon at the end, and we now have a dog class. Now check this out. If I create a dog object, it will have a Boolean variable named alive, as well as an eat method. So let's create a dog object. Dog, dog. So I'm going to display that Boolean variable. Dog.alive. If I display this attribute, this will give me 1, which means true. This dog object also has an eat method. Dog.eat, add a set of parentheses to invoke it. This animal is eating. So even though there's nothing within this dog class, it's inheriting everything from within the animal class. And we could add some additional attributes and methods as well. Maybe just a method this time. I would like to give my dog the ability to speak. So let's make this public. Void. Maybe bark. Standard output. The dog goes woof. My dog is alive and it can eat. My dog can also bark as well. It has its own attributes and methods too. I would like my dog to bark. Okay, my dog is alive. That's set to 1. The animal is eating. The dog goes woof. So now let's create a cat class. Class cat. The cat class will inherit from the animal class. I'll make its members publicly accessible. I will give cats a meow function. Void meow. Standard output. The cat goes meow. There. Okay, now we can create a cat object. Cat, cat. Let's print the alive Boolean variable of my cat. Cat.eat. Now I'm going to try and use the bark method of a cat, which we don't have. Let's attempt to use that. So class cat has no member named bark. That's because that method is found within the dog class and not the cat class. Cats have a meow method. I'm instead going to use the meow method. Our cat's alive, the animal is eating, the cat goes meow. So that's kind of how inheritance works. A class can inherit attributes and methods from another class. It helps with code reusability. You know, technically you could add these attributes and methods to each of these classes. For example, I'll just add the Boolean variable alive to each of these classes, as well as the eat method. You know, this would work too, but we're repeating ourselves. And with programming, we try not to repeat ourselves if we don't have to. Especially because if we have to make a change to the eat method, let's change eat to nom nom nom. Well, I would have to go to each class and make that change manually. And that can be inconvenient if I have hundreds of different classes. It would be a lot easier if I just had to make that change in one place. So I'm going to revert all those changes. If I need to make a change to one of these methods, I'm going to change eat to display nom nom nom. Well, then I just have to make that change in one place, instead of for every individual class. Let's try another example. We'll create a class named shape. This will be the parent class. We'll make the members publicly accessible. Any class that inherits from the shape class will have a double attribute that we will name area for surface area. Double volume. In this example, we won't have any methods this time, just some attributes. I'm going to create class cube. Cube is the child class. It will inherit from the parent class shape. So colon, public, the name of the parent, shape. Even though there's nothing within my cube class has an area and volume attribute. Then let's make a sphere class. Class sphere. There we go. I'm going to add a public access modifier. All cubes will have a double side property. Then with spheres, they will have double radius. Then I'm going to add a constructor for both cubes and spheres. Let's begin with cube. Cube, then sphere. In order to instantiate a cube object, I need to pass in a side as an argument when I construct an object. Double side. Then for the sphere, we need a radius. Double radius. I think what we'll do is that when we construct a cube object and a sphere object, we'll calculate the area and the volume based on either the side that we pass in for a cube or the radius for a sphere. Let's begin with the cube. First, let's assign the length of a side. Remember, with a cube, the length, the width, and the height are all the same. This arrow side equals side. To calculate the area, we can use this formula. So this area equals side times 6, because there's 6 sides to a cube. Then if you need the volume, you could say this arrow volume equals side to the power of 3. We could just say side times side, just to keep it simple. Now with the sphere, it's a little more complex. First, let's assign the radius. This arrow radius equals radius. Let's calculate the area of a sphere. This arrow area equals, to calculate the area of a sphere, that would be 4 times pi. Let's just say 3.14159 times radius squared. So radius times radius. Then let's calculate the volume. This arrow volume equals, to calculate the volume of a sphere, the formula is 4 divided by 3 times pi times radius cubed. So that would be 4 divided by 3.0. Make sure to divide by 3.0 and not 3, because in this case we would be using integer division. We would like to keep that decimal, so 3.0 times pi, that's 3.14159, times radius cubed. To keep it simple, we can say radius times radius times radius. And there we go. Okay, so let's create a cube object to begin with. Cube. I'll name this object just cube. Then in order to construct a cube object, we need to pass in the length of a side. Let's say 10. So my cube class inherits the area and volume attribute from the shape class. Within the constructor of the cube class, we will calculate what the area and the volume is going to be. And I will display that. Standard output area cube.area, then I'll add centimeters. Then let's do the same thing with volume. Volume cube.volume. If the length of a side is 10, the area is going to be 600 centimeters squared. The volume is 1000 centimeters cubed. Now let's try this with our sphere. Sphere. I'll name this object sphere. Then we will pass in the radius. Let's say 5. I would like to display the sphere's area and the sphere's volume. The area would be 314 centimeters squared. The volume is 523 centimeters cubed. So yeah, that's inheritance, everybody. A class can inherit attributes and methods from another class. If you have multiple classes and they share similar attributes or methods, you can place them within a parent class and all of those individual classes can inherit from that one common class. It helps with code reusability, and you don't have to repeat yourself. If you're looking for some additional practice, post a parent class and a child class in the comments section down below. And well, yeah, that's an introduction to inheritance in C++.